So the aim of this lab experiment is to remove the synthetic baseline signals using a filter designed by the pole zero method. The baseline signals are sine signals with very low frequencies 0.1 Hz, 0.2 Hz, and 0.25 Hz. The pole zero plots as well as magnitude and phase plots of the transfer functions are to be plotted in MATLAB. So what is a pole zero method? So pole zero method is a very basic method of filter design where poles and zeros are placed on the z plane. Now depending on this particular placement, an inverse z transform is taken and the time domain response of that is seen. Depending on the time domain response, these poles and zeros, the position of these poles and zeros in the z domain are changed. And this process keeps on continuing till you get an ideal filter response. So basically, it is a very trivial method where we use trial and error to get the ideal filter response. However, it is a very easy method for starting off a particular filter. See, if we don't know what filter to start out with, we can just take a basic filter we can create a basic filter using a pole zero method and use it as a primer for higher order filters. Hence, this method is useful. Now, the transfer function using the pole zero method is just this, where you'll have equal number of poles and equal number of zeros. Now, the steps for designing the filter are as follows. Now, we can place a 0 at mod z is equal to 1, which is at this point. And we place a pole for the frequency 0 Hz, where at z is equal to r, where r is calculated as 1 minus 2 into pi into fc by fs. So basically, at some r distance here, we will place a pole, and that will correspond to the magnitude response of this. Now, although you can't see it here, a lot of things get filtered out by this particular filter. Note that this 0.1 doesn't correspond to 0.1 Hz. It is actually much higher than that because this is a normalized frequency. So what will happen is this is plotted in dB, and 0.1 Hz corresponds to this value. 0.25 Hz corresponds to a value around this point. Hence, it gets severely attenuated, which is severely attenuated at this point, and hence this is the ideal magnitude response. Now, the transfer function gain is calculated by taking the magnitude response of the transfer function at the cutoff frequency. So basically, if you want to get the gain, which is G, what you'll do is at the cutoff frequency, you will make this entire magnitude equal to 1. Now then, you can compute the value of G and back substitute that into the transfer function equation. And now take the inverse Z transform. And by taking the inverse Z transform, the time domain equation is found out as a finite difference relation. Now, once this finite difference relation is computed, you can easily plug in the values, but note that this finite difference relation has to be made into a causal relation. And now, a doubt you may have is why not add zeros at 0.4 Hz, 0.4 Hz, and at 0 Hz. That is an ideal filter. However, the issue with that is the magnitude response of that goes like this. So in this case, what happens is there's unitary gain for almost all frequencies above a particular threshold. But if there's a filter which goes like this, you'll have different gains for different frequencies, because of which a normal signal, if it's like this, random frequencies will get attenuated, random frequencies will get enlarged. Hence, that is a usual filter response which you don't want. Now, obviously, even with such a filter, you can compute it and get back the original filter by doing some clever mathematical tricks, but we are currently not interested in that. So coming to the code, so basically all we have to compute in this experiment is first compute the finite difference relation, and then compute the RMSE root mean square error, as well as the SNR, as well as the mean square error. So these are all the initializations that you have, and once the finite difference is computed, this is just to add those synthetic baselines. These are different magnitudes of those particular frequencies, and we assume that our signal is a clean PPG signal. Now, this relation is a finite difference relation that we have computed using the poles and zeros that we have placed using this method. Now, once this finite difference is computed, all you have to do is write the finite difference relation and compute this finite difference relation recursively, or even sequentially for that matter, because we have a y of I that's depending on a y of I minus 1, which is depending on an x of I and an x of I minus 1. Now the error is computed as y of I minus x of I, and the sum and the addition of all of the square of these errors will be the MSE. No, this is just to compute the squares of the data, and this becomes useful when you have to calculate the SNR. Now RMSE is just the sum of all of these errors divided by the length of that, the square root of that basically, and the mean square error is the square of the RMSE. So that is what is being done here. This is for printing it out, and the multiplication of 5 is just so that you can observe the signal much clearly, and a 5 is added so that you can differentiate these two signals. So this red signal is a signal where the baseline has been filtered out. As you can see, there's very less variation. However, if you look at this blue signal, it looks like the baseline has a decent amount of variation. Hence, comparing these two, you can see that this signal is one where the baseline has been filtered out, and this is a signal where the baseline is present, the synthetic baseline that we have added. And the statistical inference is as follows. The root mean square error is around 0.28. The mean square error is 0.08, and the signal to noise error is 2.15. Sorry, signal to noise ratio. Now, the MATLAB code is this, and it is pretty self-explanatory. All you have to do is add the r, which is the radius at which you intend to put the this radius, in which you intend to put the pole. Then the zero is there is simply a 0 at 1, and this pole is basically at that place itself, at that r value. So as you can see, the pole is here itself and the 0 is here itself, and we are just calculating the magnitude response and the phase response, which is the magnitude response is this and the phase response is this. So that is the end of my video. Thank you for your time.